And so they've actually set up quite a few. There's one, he was actually the site leader here about 15 years ago. He has a 4 metre antenna, and he does moon bounces, and he also tries to detect other objects in space, and like the Crab Nebula, Centaurus A, it's a pretty bright source. The galaxy, of course, the centre of the galaxy, Sagittarius A, and so on. And he's been trying to do some interferometry into setting up two of these 4 metre antennas that he has. About 4 years ago, there was a Vela glitch. You all know Vela also. Have you detected Vela at all? No? Okay, well, project that I really recommend you do is see if you can detect Vela, the pulsar. It's the brightest pulsar in the sky, and it should be detectable with an 8 metre antenna.
How frequently does it pulse?
11 times a second.
Oh.
11.123 seconds. It sounds like this. Exactly like that.
So do you know what the radio spectrum is from that?
You get it any frequency.
Because
What's your antenna for?
1.4.
Oh, perfect. That's
okay.
yeah, that's perfect.
4 and 23 close than
I can even give you the fluxes for that. You're looking at like 1,000 Jansky source. That's how strong it is. Okay. And you can get even great, stronger pulses, because it does vary. Sometimes it misses a pulse and so on, and other times you get a really big one. But you're looking at around 1,000 Janskys.
So John,
If you can't detect that, you won't detect anything.
when you say you made a sound effect of the sound of it,
Yeah.
was that what we would possibly detect with
No, you don't want to listen.
As a live...
Well, you could listen to it, but you'll probably have too much static in there to hear it. But what you want to do is just do what you do is just take a voltage jump of the signal you're getting, and then fold it on the period of the pulsar. Okay, and you should get peak at 11.12.
So we could do it. We could do an autocorrelation essentially.
Oh, what? Sorry.
Autocorrelation.
Not an autocorrelate. I've already got the one. But just take a what you can do if you can get a voltage jump, just have a file that has nothing but voltages, time series. Okay. I can speak to some colleagues who can give me software that allow you to read that and then produce the plots that you want. Because that's pretty straightforward. And you should be able to see the Vela pulsar there. Because one of the projects we're trying to do is see how small an antenna do you need to detect Vela. Okay. We're trying to get down to 4 metres or something, but if you've got 8, it'd be good to see if you can...
8.5.
Sorry.
He's our engineer.
So,
And that's not millimetres.
So John, I've got a background in physics actually. I worked at CSIRO in Clayton
okay. You probably know more than I do on this.
until Tony Abbott came along. Sadly. So if you've got a paper on, I'm taking a look at it and see what we need to do just to extract the signal. Or...
Yeah. Well, I don't know if there's a paper, but I can put you in touch with.
Yeah, that'd be great.
And they can advise you. I said 4 years ago. What is it? February the 4th. What's today? The 3rd. Oh, okay. 2004 years ago, Vela glitched, and I had a monitoring program here with our 12 metre antenna to detect it, which we could, and unfortunately, just days before, the digitizers failed, and I said, "Oh, I'll have a look at it on Monday." And on Friday night, pulsar glitched.
So that's how you work. That's how you get it to glitch, is it?
Right. Yeah, just shut down for a few days and it was guaranteed it would glitch. So what happened was, we wanted to know when exactly it did, because when we looked at it later, it's glitched. When did it happen? I'd taken data a few days earlier.
It's changed its shape.
It changed its period. It spun up. So normally it comes down, I think it's slowing down, very, very minute, and then it speeds up.
Yeah.
Speeds
You
up.
can tell.
And that's called a glitch. Yeah. And so we wanted to know when it happened, you know. But I had a few, and Hobart, we were observing it at Mount Pleasant, but they had problems with their instrument. That tells us their bearings have
The aliens don't need to feel
and,
you're not listening.
and Malonglo were looking at it too, but they were shut down again also for a few days either side. So we didn't know when it happened. However, in Sydney at Epping, one in the middle of Sydney, there was an amateur radio astronomer, Steve Ullman. You know Steve Ullman?
We don't know him personally, but we know.
He had a system set up, just simple Yagi antennas, set up as a transit instrument, and every day Vila would pass through his beam, and you would get a few minutes of the what do you call it? You would see the pulsar
Because it
for a
wasn't
few
tracking,
minutes.
it was he?
It wasn't tracking, it was just a drift scan. You just had it fixed and it would drift through his beam. And he actually caught it. It happened in the period that he was transiting.
Oh, geez, that's like.
And he didn't know what had happened. He thought something weird had happened. So he contacted and said, "Oh my God, he caught the glitch." And we knew within a few minutes of when it had actually glitched. I said, "Oh, thank God." You know?
Yeah, I read that.
And so we were going to write a paper on it and so on, but and have him on it, but all sorts of things sort of intervened and we never got around to doing it. So but it was on the ATEL and Astronomical telegram, and but that's something that is really useful because astronomers we don't have time. So the thing that amateurs have that is professional astronomers don't have is unlimited time to observe. You know, most amateurs will observe 24 hours a day if they could. If the sun wasn't up for 20, you'd do it all for that whole time. And so you have time on instruments that astronomers, professionals don't. Because so an astronomer applies for time on our telescope, maybe even 2 or 3 hours, or maybe a few days, you know, in a month's time or something. They can't sit there for continuously doing it. At Mount Pleasant, they had a 14 metre antenna that would track Vega for I think 14 hours a day when it was above the horizon, and they in the hope that they'd catch a glitch, and in that whole time they only got one. Okay, with that antenna, but with the 26 metre, the one in 2016. They were actually observing it with the 26 metre when it glitched, and so for the first time they were able to see the individual pulses during a glitch, which made Nature. It was published in Nature. That was quite a significant observation.
How long does a glitch last for?
It's with about 2 or 3 pulses. So in the space, which remember, each pulse on Vega is 33. The period is what is it?
Said 11 times as
11.
so
I've got 90 milliseconds.
I've forgotten 80 something
Five.
milliseconds. So so in the space of just a few pulses, it glitched. So we know because before that, does it take 5 minutes? Does it take 10 minutes? Is it an hour? What is it?
one.
But we found that it's just a few glitches, a few pulses, and it glitched, and so that was significant.
So that's a rotating neutron star?
It is, yeah.
And the glitches are presumably local earthquakes?
Well, they're not sure what they are. That's why we want to find them, you know. There's various theories, you know, that there's some, that the crust of the neutron star is coupled somehow with the super fluid interior. It's most of the time they're coupled, but occasionally it sort of slips, if you like, and speeds the spin up a little bit. But that's a project that would be very useful to look at that. Vega especially because it is so bright. There are other pulsars that glitch, but they're fainter. So you could maybe try, if you could detect some of those with an 8 metre, maybe you can monitor those also, looking for glitches. So another project that I wanted to start before the pandemic began was using our 12 metre to just observe a single point on the sky for a long time. Because a small antenna has a relatively large beam. Okay? 64 metre has such a narrow beam, you wouldn't waste your time on it. But a small antenna, 12 metres or so, gives you about a degree or so on the sky. With your 8 metre, what's the
1.7.
1.7? So
Depends on the frequency, sir.
Oh, yeah, frequency, but your frequency at L band, it's about, what, 1.5
Yeah.
degrees, yeah. And so, and so my idea was to just observe one single position on the sky and rate just continuously, and at the same time,
Tracking or just fixed?
no, track that position on the sky. Okay, and then at the same time, optical astronomers would look at that same position and just image it continuously. Maybe do, 1 minute integrations, dump it, do another minute, dump it, and so on. And the reason we want to do this is that if we find a fast radio burst, okay, we'll be able to, if it does have an optical counterpart, we'll be able to see it. But of course, we'll only be able to do that at night.
Yeah, but also, like 80 milliseconds or a very short times for taking images.
No, you don't want to do, no, the image will just be a constant, like a minute exposure. And if something bright suddenly appears, it'll just appear as a dot. So if you then time lapse it, we go, oh, it appeared there, and then see if it corresponds to the time that
Within that minute or so.
yeah. Although because of dispersion, and the distance, it could be a long time between when you see the radio pulse and when you see the optical.
So how likely is it to happen?
Well, the theory is, we discovered the first one in 2007, and up until about 5 years ago, we had the majority of them, over 20. I mean, I found one, which during the course of my observations. But now there are thousands of them.
So those just is there a particular part of the sky?
No, they come from everywhere. They're everywhere, and the statistics suggest that these fast radio bursts, there's thousands of them going off every day. Random positions on the sky. But you have to be observing at the right time, the right position, the right frequency, and you have to have the equipment that can find it. Because if you're just doing a long integration, you're not going to find it. You need high-speed data capture to see, oh, there's a spike there.
Millisecond long.
Yeah, just as fast as you can do it and how much disk space you've got.
So your experiment is assuming that it does give optical.
That's right, yeah. I think there have been some.
They have been.
I think there have been.
They have.
But generally speaking, the radio telescopes are looking and the optical telescopes aren't looking in the same places.
Yeah.
So it's happened to be,
But because of dispersion, if you see something and you can get a telescope onto it pretty quickly, you might be able to see the afterglow of it.
The problem with an optical telescope is looking at a section of sky is you get all sorts of cosmic radiation, you get...
Yeah, that's fine.
You get
That's fine.
radioactivity, so unless you knew that something else could correlate to it.
Well, that's why if you know something's gone off,
Yeah.
then you go looking for it and says, okay, then it's in that. Let's see what's there.
See, normally if I stacked my images, the standard deviation would throw that data away.
Yeah, exactly. But that's what you don't want to do. You don't want to do that. And in fact, that's how pulsars could have been discovered decades before they were. But people were smoothing the data.
Yeah.
There's a lot of bloody current ignition systems ruining the data, or just too much noise in the data, so they smoothed it. Because, and as a result, they missed the significant observation, discovery. But Anthony Hewish was building in the UK, building the
Jocelyn Bell.
she was a student. He built this instrument to detect interplanetary scintillation. That required high-speed observations, no smoothing. And so he got one of his students, Jocelyn Bell, to have a look at it. That's what you give students, the boring work to do, through miles and miles of paper tape, not paper, chart recordings. And she found what she called some scruff one day, and then dismissed it. And then when the next day it appeared again, she realised, it's 4 minutes earlier. And as every astronomer knows, from Carl Jansky, if you see something 4 minutes earlier every day, it's coming from the sky.
from a fixed point as well.
Yeah, well, because it was a drift thing, so yeah, she knew where it was and so on. And so they came back and had a look and did a higher speed,
Yeah.
higher resolution recording of it and found the pulses. And then, you know, but they didn't smooth the data. So a lot of, you probably missed a lot of great discoveries. Always have to be careful. I get nervous when I throw my
Oh,
book
it's
data.
really great discovery, believe me.
So that's one project that'd be really good. Those two, try and observe pulsars for glitches. I mean, it's great to observe something and it's, I've seen it,
Yeah.
but so what? You don't want to do something with it. So you want something that'll be useful. So observing Vela, which is a pulsar, you get the kick out of seeing a pulsar, but also you can do useful work, scientific work on it, and say, we're looking for glitches, and you can contribute to the science that way. FRBs, although now we've got instruments, we don't probably need it anymore. It really should have been done about 4 years ago. We had people set up to go when the pandemic occurred, and now Chime in Canada and other instruments are finding hundreds of these.
What was that?
The instrument's called Chime.
No, you said FRB?
Fast radio burst.
I mean,
Are they found in the radio burst or the optical equivalent?
Well, they're all found in the radio first, and so that's why we call fast radio burst. And people wanted to know, are there equivalent in other frequencies, in the visible, ultraviolet, gamma
So have
rays,
they
and so on?
confirmed any others?
Yeah, I think there's been a few in
There's
the
been
gamma
probably
ray.
not very many,
Not many.
They,
Only a handful.
they have
And we're
found
still-
repeaters too.
They have, yeah. Some of them repeat, but not necessarily regularly. So they just occur, but there's no periodicity to it.
Doing science.
So it could be some form of magnetar that's just giving out a burst every so really strong burst. It has to be some humongous burst because these things, depending on the dispersion, they're billions of light years away.
But how do you know the billions of light?
From the dispersion of the signal. So, that was the clue that it wasn't a local interferer. Because as soon when it was first found, and I was told, I said, it's like interference, And then he said, no, have a look at it's dispersed and broadens with frequency too. So the width of it is frequency dependent too, which indicates that it's travelling through some medium to get to us. It's not local. And so that's why it was taken seriously. But for a few years, no one had found any other one, because no one was really looking for it. And then suddenly in the data, another one popped up. That's how these things are usually discovered. You're doing one thing and you discover something else, serendipitously. So that's one project. There are other projects you can do. I'm more in the pulsar, so I'm just thinking in terms of pulsars and so on, because that's where you really can do something useful. To do just continuum scans of the sky.
That's where it started on that.
Yeah, and that's great, but I don't think you'll find anything new.
I don't think we're interested.
Yes, we will.
Yeah.
Because we've never done it before.
For us, it's new.
New to us.
And it's a good, but also the project, for me, from my perspective, I want to do it to teach people radio astronomy. We have teachers' workshops, and it's always optical instructors. Why are we doing optical? Anyone can do optical.
We're here.
I started off optical. Okay? You do a Google search, you get all the optical stuff you want. Telescopes. Everyone has a telescope and whatever. But how many people understand radio astronomy and how to do it?
One or two.
Exactly. So we want to get it out more. We're a radio astronomy institution in the Australian Telescope and Action Facility, and I think we should be concentrating on explaining radio astronomy to people, and a good way to do that is to get the teachers to do it who will then teach their kids, and so you need to get it into an inexpensive sort of form. My idea was to set it up as a project where you have the teacher will appoint someone to be the project manager for the project, and then you have someone who's really good at electronics to put it all together, someone who's good at coding to write the software, someone who's good at carpentry or whatever, metalwork, to build the
We've got all
antennas.
that. All those boxes.
And then you have the physicists sit down and analyse it.
That's it. We've
But
got
yeah,
everybody's here.
So in other words, you're teaching the kids not just radio astronomy, but how to
Bring
do a
project.
project. And bring everyone together, do it as a team, and so on. And so that's trying to push it for 20 years or so. And it looks like it's like with the SDRs now, it may actually take
Makes it a
off.
lot easier,
Yeah.
doesn't it?
Yeah. And so our guys at Epping are developing new little antennas they could use for that. But one thing that we want to try is just get a dish antenna, 4 metres, 8 metres or whatever, put them into these things and see what we can detect.
At the moment, we're using a fixed hard
Yeah.
receiver,
Yeah,
which then goes to a serial.
which
port.
I've seen on, yeah.
Yeah, and the idea of putting the software
So
design.
you got RS232?
Yeah.
That's
I know, it's really.
I did that in the Yeah.
Yeah, it was
So-
early.
I mean, it's perfectly good, but I don't think you'll get the data right.
Yeah, so there is thoughts of putting an SDR in place.
And you can trial that reasonably easily.
Yeah.
And then really your concentration's on your LNA, your low noise amplifier.
Yeah, we've got questions and things about all that.
Yeah, I was going to ask if there's any spare ones at Epping that you might.
A lot of these things are reused, yeah, because they can be quite expensive to buy off the shelf.
I was being cheap.
Yeah.
But also serious.
Well, I've got to say that there's also the same thing happening in that microwave LNA environments where their costs are dropping dramatically. Yeah. There's some stuff now that we're buying off the shelf instead of building ourselves for our new instrument. That off the shelf is easy and it does all the performances that you need and everything else, and it's quite good.
Actually, so just on that, would we be able to get a few model numbers, the sorts of things that you? Oh, we've got one thing.
You just need to find out where their shelves are.
What we've done,
We've all
one of the students that's doing the summer scholarship in Epping, I was hoping they'd be here this week. There were plans on coming, but they just can't get the schedule right. One a supervisor can't make it, so it's not coming. But I was hoping they would. But basically, we get these SDR spectrum analyzers, and all you do is just plug your antenna into it.
So at
And it's all
1.4,
up. Yeah, whatever the. Well, this one he goes from.
I think it goes from 500 kilohertz all the way up to 9.
We go plenty, the ASV.
Plenty.
But that's the Tektronix one, so that's expensive.
It's
Yeah.
expensive. You can get others.
But the SDR and the LNA at the front, the amplifier at the front, that's pretty reasonable. And cooling it is the other piece for the amplifier.
So when you call them, do you use liquid nitrogen for that one? Or?
No,
Helium.
Sorry?
So on the telescope, all the receivers, all the front end of that, are cooled down to 23 K,
22.
22, 23, something like that.
So you
Kelvin.
use
Kelvin.
helium.
really
Yeah, they're super.
Yeah.
And no. That's and it's probably not worth doing that, because your noise around you's going to swamp you more than that.
yeah, and plus it's our receivers. It's the LNAs in the dura of the receiver that we're cooling. You won't have that.
No.
You just have ambient temperature receivers at the focus, right?
That's
We're
correct.
talking about putting a Peltier,
Peltiers.
trying to reduce it down to about
Oh, that's okay.
more.
Well, if you can get the noise level down as much as you can, that's great. You're not going to be using anything too sophisticated. But it should be good enough. What you've got should be good enough to detect V or 8.5 metre.
Yeah.
So no problem.
So doing all the cryogenic stuff may not be worth the expense of doing that for the dish that you've got. However, as soon as you go down below zero, you're going to have major problems with cooling, ice, all this stuff. I have seen some people use dry ice to actually cool their units, and it gets the noise down, and might be a little bit of an advantage. But I wouldn't go out of the way to do that.
Because the optical group always, a lot of their cameras are sensors are all cool to
Yeah, but
reduce that on the.
But that's because with optical you get the heat signature.
Yeah,
That's
so
what CCDs are sensitive to. What
Yeah.
are they sensitive to in the radio?
Thermal noise.
Just resist and resistance.
Yeah,
So you try and cool that
Yeah.
to minimise the, what do you say, the static in the thing. You want to drop that so that
But it's not
fancy.
infrared though, is it?
But the other
And that's radio noise.
Well, any charged particle that's accelerating will emit radio. Okay, so when the atoms in your electronics are warm, they're going crazy, okay, and you hear it sound. But by cooling it, you're
It's obviously a different type of radiation, but it's still the same.
yeah, it's just
Yeah,
not
yeah,
radio.
yeah. And it's that signal to noise that you're trying to get. You're trying to get that noise floor right down so the signal pops out.
Yeah, I just had no idea.
the other
It's the same problem.
Yeah.
So you've got noise. So you've got noise in metal, and that's thermal noise.
Yeah.
So that's got a spectra depending on the temperature. Then you'll have every semiconductor that you have. Every point where the two materials stuck together will have a noise, and that has some functions. Usually it's thermal, but it's more than that. So that's shock noise in there. So you're trying to get all these little additive noise levels trying to come down
The-
as much as possible.
the other thing is you need to be able to create a consistent value. If you have something that's monitoring and maintaining a consistent temperature, that's what we do with the optical. Is you say set it at 12 degrees, and you'll see your fan or the power to it will go up and down to make it negative 12 degrees, and it'll stay there, so it's always consistent.
We deal with that by subtracting the signal from a data frame, right?
Yeah.
Which is obviously different to here.
No.
Oh, you do the same thing?
You
Right.
do the same.
Yeah. So some of the problems that you're going to have with your Peltier is that's the semiconductor.
It's going to create
It's going to create noise, and it's right next to your receiver.
Oh, okay. I haven't thought of that.
Yeah.
I've used them a bit before. I haven't.
Yeah, so with our instruments here, for when we go do cryogenics, our compressor is in the tower at the bottom. So that compresses the helium up to 380 psi. That goes up to the top, and then we have a refrigerator. It's basically a Stirling motor that just expands the gas and cools everything down. But that is actually at least probably a foot away from that and shielded, completely shielded, so that we don't get any feedback. And that's actually pointing to a finger that touches the unit. So, and that's in a vacuum.
Yeah.
That we have, which is a really strong vacuum that we have in there. In a steel case, again, a stainless steel case. So there's shielding on top of shielding on top of shielding, just so we can get that finger to cool down to minus, to 23K. And we're only cooling something that's probably about a centimetre square.
Is that all in the vacuum?
Yes, and it's a hard vacuum.
So you're constantly pumping a turbo.
Because otherwise,
So we do a turbo pump, which is roughs it.
Yeah.
And then we have ion pumps.
Oh, okay.
sounds like it would weigh a lot.
Well, the receiver's by half a ton.
Yeah, but it's probably
As weighs kilo or two.
All that, so
Yeah.
it is. It's a milled stainless steel container that we have. So our prime half, which is
I think, yeah,
sort of that big, that's the receiving area, is a massive piece of steel,
Mm-hmm.
stainless steel that we have to build on. And when they first built it, it leaked. So the guys have been working really hard trying to get stop the leaks. Yeah.
I'm so pleased to hear you're human because we have all these problems.
I mean,
these
these are all bespoke pieces
These are
of kit.
opportunities, not
Yeah,
problems.
not off the shelf, not off the
I
shelf.
They're off the shelf. Yeah. So.
What you should be concentrating on is just with the equipment you do have, just detect things first. You know, get that working, and then once you've got, then you can think about improving the system temperatures,
Yeah,
signal to
okay,
noise
yeah.
ratios, and so.
We do have an issue with drift of frequencies and noise levels when the sun comes up.
Oh yeah,
Hot days, cold days.
yeah. Well, what we do when we do an observation, we usually do a calibration on a cal, where we have a little noise diode in the receiver,
Yeah.
which we turn on and off. we know the power exactly of that because we designed it, okay? And so we sample that, and usually it ends up being like a little square. You produce a square wave. Okay, so you have when it's off and when it's on.
Yeah, of noise, a square wave of noise.
Of the diode, the signal that you've turned on and off. So that way, the units that you use, which are quite arbitrary, we can say, okay, this is the zero at these units. This equates to so many watts or whatever. You know? And so when we then observe a pulsar right afterward, then and we want to calibrate it. We want to know exactly how strongly it was. We don't want arbitrary units. We want to know exactly what the power was we received. We can then use the cow to determine what that was. And then when we do another, we do it again. So every observation we precede it with a cow. Because it does change.
Whereabouts in the chain is your dials, your noise dial?
Sorry?
Whereabouts in the chain is your...
I think it's at the front.
To Steve here, 'cause
Yeah.
it's like the proper questions to ask.
Yeah, I think it's up at in the receiver.
It's in the receiver. When you have a feed warn, it's right next to it. It's actually in the feeder.
It's in,
Okay, so that's right, so it's taken in there.
Yeah, it makes more, because you don't want to have, because you want to come down the same signal chain, so that you don't introduce something new that because you want to calibrate what it is you're receiving, you send it through the same signal chain.
Do you bother also to switch to a dummy load, a dummy reference, to have a receiver base?
We do that hot cold test, and when we commission the receiver, so we have a good idea of what it is.
So the main thing is to switch from the source to a
Yeah,
reference.
like you go to a bit of empty space next to it, maybe a degree away, okay, and do your count.
Yeah.
And then go to your source. You don't want to be too far away because then because if you're too far away, you'll have get a different result because you're looking through the atmosphere. You might be, a bit of the Milky Way in the wavelength or something. So you want to be relatively close by, but away from it. You don't want it in the beam or even in the side.
Side lobes.
One of the side lobes. You want it just off. Do it there. When you do it, then switch over to your pulsar and observation or whatever it is you're doing.
So in the optical side, that's your dark frame.
Yeah.
So if you do it from the observing and then to the sky, you're just doing a reference of the sky. When we do it with the noise diode, we actually get a calibrated figure. So what we then go to Jansen's.
Can we have your circuit for that noise?
I don't know, but I can put you in touch with people who do it.
Please?
Yeah. Maybe they could even give a lecture to you guys on Zoom or something, how you would do it. Great. But they're flat out, that's the trouble. They're very, very busy, but
So
they ask nicely, they might, I'll ask them and see what they can do.
Yeah.
So they're the guys up in Sydney.
Yeah.
Happy to email correspondence.
We did have an RF engineer here, but he retired 6 months ago, so unfortunately, he would have been great too. He would have answered one of those. I'm not an RF engineer, so I just use it.
Yeah.
Can I ask a question, sort of related, but different in that, in an optical telescope, as the temperature drops during the night, you have to do occasional refocuses, right? Do you have a similar problem with radio telescopes?
Yeah, well, when you're very high frequency, we have to constantly check the focus and the pointing of the telescope. So we would, and especially if you're doing VLBI, because you need to be really spot on.
So you
But at
change-
very, very high frequency.
Yeah.
But at the frequencies we operate at, it doesn't change that much. So when we install the receiver, we would do a focus check and a pointing check, and then leave it. And it won't change significantly
So
over the. When we take it down and put it back again, we'll do it again, but we only do. But if it's very high frequency, like we'd look at the Mars receiver or something at 8.4 gigahertz,
You need to worry about it.
you need to worry about it. So you've got to do
and that's
quick check it.
because your wavelength is going to,
Obviously,
all
small.
these shapes move
Yeah.
in that wavelength.
Yeah, your focal plane or the focal area on the telescope is much smaller, so any deviation you're going to notice it. Whereas at L band it's quite large, and so if you're moving a little bit,
But it's a big dish.
Yes,
That's what I was thinking, you know,
Yeah.
there has to be a lot of expansion going on there.
it is, but it's been measured and
Yep.
we account for that.
And you won't-
Do you know how much it does expand?
Oh, I'll have to look it up. What, expand? Oh, I
Yeah.
don't know. I mean, what it does, the dish, when you tip it, of course, it's going to warp under its own weight. It'll never maintain the perfect shape, no matter what you do. But we have measured the deformation of the dish as a function of tip angle, so we know how it would tip and how it would deform, and they've discovered that it's what's called a near-homogeneous dish. So when it tips, it doesn't just tip into any old jelly shape, you know.
It's predictable.
Well, not only predictable, it actually warps into another parameter. So basically, you're just opening and closing your parameter. So when you open and close a parameter, what happens to the focus?
Shifts up and down.
Moves up and down. Okay, and so if you know how much it moves as a function of tip angle, then just put your receiver on that part.
We're actually looking to do.
Oh, for yours, I wouldn't borrow it.
I'll take that.
Take that off, boys.
Unless you're going to really, really high frequency, but
Steve has some.
at all band, I wouldn't.
So John, what is the actual range of the Parkes dish, frequency range?
Oh, well, in theory, we could go up to about 115 gigahertz, which we did in the past, but when we put the new focus, that's the old focus cabinet, when we put the new one in, see this solid interior, that central bit? They used to use that at really high frequencies, so, but in 1995, we put in a much larger focus cabinet and double the size, so block too much of that solid area in the centre.
Oh, yeah.
So we stopped observing at those really high frequencies.
How low does it go?
Up to 64 metres, we can go up to about C-band, which is about 6 gigahertz.
Yeah.
From there on up to maybe 22 gigahertz, which is the highest frequency we currently observe at. It's the inner 55 metres.
What about
2000, but before 2003, it used to be only 45 metres. We increased it by 10 metres in 2003. So, and I can show you the panels outside. Originally, when the surface was built, the telescope was built, it was made up of steel wire mesh panels, which was suitable all the way up to S-band, about 2.33 gigahertz or so. But beginning in 1970, we progressively replaced the inner 55 metres with perforated aluminium panels. The first one, you might see one of the pictures coming up shortly. In 1970, they replaced the inner 33 metres with the panels, aluminium panels, perforated aluminium panels. And then in the 1982, they went out to 45 metres. And then in 2003, we went out to 55 metres. So currently, when we're observing the high frequencies, it's actually a 55 metre antenna, not 64.
So how low do you go
What do you mean?
in frequency?
Oh, well, we can go as low as you want, but there's a lot of rubbish down there now, so we don't bother anymore. There's mobile phones.
You don't bother even at neutral hydrogen?
Well, the lowest we can go, depending on the job, we do have a UHF receiver where we're around 405 megahertz, but that's for spacecraft tracking, very specific, like the Curiosity rover on Mars. And that's just room temperature receiver, it's nothing sophisticated about it at all, just very big. But the next, our ultra wideband low receiver has a frequency range of about 700 megahertz up to 4 gigahertz. But around L-band, it's just shocking. There's a lot of interference and everything else. It's not very good. Because it's all mobile phones, Wi-Fi, and Bluetooth, and digital TV, digital radio.
So my next question relates to that frequency range. What antennas are used up at the feed point?
The receivers, you mean, up there?
Yeah.
Well, that's it. We have the ultra wideband low. And in the past, we would have several receivers. We'd have one at 50 centimetres, which is what, about 700 megahertz. And then we'd have one at around L-band, which is about around 1.4. We have one at S-band, around 3 gigahertz. And then we have a C-band, around 6, and then the X-band, and other things, even other smaller, more specific antennas for other things, like we have the HOH receiver that could go from, they have sort of weird sort of frequency range to be able to observe the hydrogen as well as the hydroxyl molecule.
Sure.
From one point, hydroxyl was around 1600 megahertz. So we needed some, but the bandwidth of the antennas in the past would have been around 250 megahertz or so like that. Now with the ultra wideband, it's 3.3 gigahertz, and we're even planning, hopefully if we get the funding, get ultra wideband high, and we'll go from 8 gigahertz, 4 gigahertz up to 25 gigahertz.
So do you have to swap these things out to do a
You did in the past,
yeah?
because we have a translating device up there. It's a little platform on which we can put up to 4 conventional receivers,
Okay.
and then just by pressing the button, we can put any one of those onto the focus very
Okay.
It's a bit like having filter wheel.
Yeah.
Yeah, basically. Yeah.
Okay. So
And
mechanically moving the position.
but some of the receivers are so large they take up a whole one side.
Okay.
So like the ultra wideband height takes up one band, and then we've got room for 2 others on the other side. At the moment, we have the Mars receiver, which is our X band, 8.4 gigahertz sitting there. But we did that. We developed that wideband receiver so that we wouldn't have to change receivers all the time. We just tuned to where we wanted. In the past, it was like if you wanted to listen to the ABC on one station, you have a radio just for the ABC. You
Yeah.
want to listen to another commercial station, you'd have another radio just for that frequency and another one for that. And so you have to literally go get the radio and turn it on to listen to that station. So, and that's how we used to operate. But now with the wideband receivers, we can just tune to where we want, like you would on a normal radio. And just dial up, oh, I want to go to that station. Or get the whole lot all at once if you want.
So with the wideband receiver, is this like a feed horn? You still have a feed horn?
Yes.
We do, yeah. It's for a special feed horn that's sensitive to that.
It's
radio.
broadband.
Yeah.
Yeah.
And then there's also pretty sophisticated electronics.
I was going to say, and then usually at the end of the feed horn there's a monopole antenna or something to pick it up.
Yeah, you have. Well, we have our receivers are linear polarized.
Yeah.
So in other words, you have the feed horn that comes in that directs the radio waves in, if you like, the radio. And at the end, you've got these 2 little probes, 90 degrees to each other.
Orthogonal.
Your orthogonal, yeah. And so this will pick up the polarization in that direction, and this one there, and you have your 2.
And so is the shape of the horn designed so that you get essentially the maximum of the signal?
Yeah,
These
and
antennas
for as
over that-
broad a band as
over
you
that
can.
broadband?
Yeah.
Yeah.
Yeah,
So
that was
it's something
CSO
you
road
get-
designed and developed in the 60s.
Oh wow.
There was one that was used for the Apollo 11 mission. But now they're all corrugated and so on, and that allows you a special way to get that broad.
Oh, okay. So yes,
So-
because otherwise the bucket's the wrong size.
So the feed
Yeah.
horn
Yeah.
itself has got a slug in the middle, and it's
Special dielectric.
a special dielectric. So it's got the normal polyethylene stuff, white, and then inside there's a quartz mix, polyethylene. So your dielectrics are all this thin that gives you this flat response over the whole
Mm.
band.
I think, do you end up with a lower sensitivity across a wider band, or?
No, no.
Well, no,
So-
it's
so
actually
that-
the opposite.
That feed horn is tuned in such a way so that all the different frequencies will all come in at the right levels coming into the receiver.
That is clever.
Yeah,
Now,
because
But
normally.
it really think it's big and heavy. It's big.
Yes, that sounds like a real sort of magic pudding job to be able to get.
so you have these 2 linear polarized signals as a result, right? Of the linear polarized signal coming down the 2 channels, right? And of course, as you're tracking something across the sky, if you have an outhouse mount, what mount's yours? Outhouse?
Yeah.
Okay. You're going to get field rotation.
Mhm.
Okay. So the angle of
Polarization.
polarization on the sky will change.
Yeah.
Okay. And so you're going to have to
Spin,
rotate the thing to compensate for it.
spin the antennas.
Yeah. No, not the antenna, just the feed.
Just a feed horn.
The feed horn is what.
Yeah.
Yeah. Or the antenna.
Yeah.
You can do the whole thing if you want.
Whole thing.
So if you can rescue antennas in Western Australia, the whole antenna rotates.
So the whole dish rotates to do that.
That's a bit much for us, but
Yeah.
turning
Well, on ours,
turning the things.
of course, we're not going to spin rotate the dish, but the receivers, they're sitting there and we can turn it. So if we want to maintain a constant parallactic level on the stride, we just rotate it.
At the very moment, we've just got the one monitor,
Yeah, that's good enough, honestly.
so we don't need to rotate it for that.
No.
Not yet, Phil.
No,
We'll come to that, but we'll start looking at polarization.
Yeah, you just want the total power coming into the thing, that's it. And that's how they used to be in the past, you know, they're all like that.
I have a question with regards to our motor drives on our system. We're using SCW multi-track, which is
I'm the
a
wrong person.
variable speed drive.
Yeah.
And it's creating noise down at the 20 megahertz range, which puts our Joe into a lot of trouble. Should we just shield it and shield it and shield it until it stops? Or is that?
Yeah, you can have troubles.
Yeah.
So,
we do.
So they're DC drives.
No, it brings in single phase AC into them and puts out 3-phase to the servos.
You should.
1.5.
So, how far away is the driver? The
The drive from the motors
Yeah.
is about 50 metres or 30 metres or something.
It'd be about 50, including all cabling.
Corners and
Yeah, and up
through
and down.
under and over and like, yeah, it's probably 50 metres.
And what frequencies does the output for the that drives the motor? as
It's the like 50 hertz to
Direct 50
80
hertz.
to 20 hertz and all that sort of.
What
Uh,
is it chock? What did you use at 20 megahertz? What
well?
did you
Okay,
say?
so if
That's
it's
the Jove receiver is 20 megahertz and
Oh.
the switching of the motors drives is at somewhere in 5 kilohertz, but then you got all these
All the harmonics.
harmonics and
Wow.
yeah.
so on.
We did ask for filtering and everything, but they.
So one of the things, it's going to be a little bit of a illusion. Hopefully you've got an electrician with you.
Not here, but I can sort of.
Okay. You know the IEC leads that
Yeah,
go into
the plugs.
yeah. You'll find that a lot of those will have a H, what we call a H filter on it.
Mm.
Just
So,
filter
yeah,
the
the
wire out.
coils and the capacitors.
Yeah. So in the actual unit itself, if you can, each individual phase goes through one of those
To the motor.
to the motors.
Yeah, I asked for SCW to supply us with something like that, and they said, "Oh no, we don't do that."
Yeah.
But
so,
okay,
so,
okay.
so,
I'll
but
talk
the
about that.
danger you're going to have is that if your frequency chopping goes higher than probably about 150 hertz,
Which
that H filter will chop, will take all that power.
and all the power will drop and it'll store the motor.
Yeah.
Yeah. Okay. All right.
But you're going to have to do some weird. So most of the times, what you'll find is it depends on how it's chopped, how it's doing. If it's doing, a lot of controllers will do it really badly, and all they have to do is they get the AC signal and they chop it really well.
Well, I think this converts the mains into DC and then DC to the.
And then a variable pulse width modulator.
Yeah. Oh, it's a sine wave out, but it's like you say, it's going to be chopped all the way out.
Yeah. You need to have a look at it. Have a look at that signal and see how bad it is. You can shield your power cable
Yeah.
going up
With
to the units
They are shielded all the way.
with proper earth.
Yep. And we try to connect the earth as many places as we can for.
So I mean, you can keep on doing bits and pieces like that. The actual motor itself is probably another place to look at.
Yeah.
As the signal goes into the motor the shell itself might have problems because you probably have to feed through to go through there. But that'll be probably where your radiator come up. Because all that cable going into the motor is one big it's one giant antenna.
All right.
John,
Yes.
another important question about your beautiful instrument out there. What's the limit of sensitivity? What's the weakest signal it can detect?
Well, it's a question of how long you want to integrate your signal. A lot of this
About
stuff.
a real-time measurement then.
Depends on what it is.
There is a pamphlet we got from
There
the,
is some, like for example, there was some pulsars discovered about 2 decades ago in the multi-beam survey. And, you have to sit on the pulsar for like an hour or so or more to even start to see the pulse through it. So, It just depends on what it is you're observing.
There's a pamphlet we got from the place we're staying at in Parks, and it stated 10 to the minus 14 watts as the power they were detecting.
I don't know where that. Oh, I saw that. Yeah,
It didn't qualify the,
it wasn't
qualify the
very-
bandwidth or anything.
Yeah, it was. I saw that. I'll give you. Let me see.
Isn't that that's the same thing where the demonstration is you drop a piece of paper and the force that it hits the ground is more than the equivalent of all radio signals we've received from outer space.
I'm trying to understand the level of sensitivity to receive plus the gain of your antenna. So I know it's wideband and so forth, but what if you converted that to a single carrier a signal
Well,
generator?
put this one Jansky source for us. One Jansky source is 10 to the minus 26 watts per square meter per hertz. And that's the flux that we normally. One Jansky.
And you can detect a jet.
Oh, that's easy. Yeah. So, yeah.
We're down to micro.
We're down to mini Janskys. Even lower.
That's what I want to know.
Yeah. Vima is 1,000 Janskys, which is why you should have no trouble.
That's for the less than.
And to answer your question, I think I got right.
dBms, milliwatts, microwatts,
Okay,
microvolts.
So
Yeah,
10 to the
yeah,
minus
so
26.
we're down 100, 110 dBm.
Is that all?
No, more.
Minus. So we're right in the noise.
I did the calculation for our 8.5 metre based on the sensitivity of our neutral hydrogen receiver and then the gain of our dish, that the signals we're detecting, which are creating a blip in the receiver, were minus 164 dBm. But that's if you took that accumulated noise and converted it to a carrier, because I've tested the receiver with a signal generator. I'm an RF engineer, by the way.
Yeah.
So we're seeing the same response in the receiver from the 6 megahertz bandwidth continual mode of the hydrogen receiver. And that's producing, say, 2 volts output.
This is with your 8.5 milliwatt kilowatt.
Yes, yes. So I did the calculations and converted it back and said, well, that's equivalent to a signal coming from space of minus 164 dBm. How does that sound?
Minus.
And I put it then in other terms,
164.
which was 40 zeptowatts.
So what?
Well, you know,
We can work it out later, and I'll show you.
I'll have to look at the calculator, but like Apollo 11, the signal was minus 190.
Okay, fantastic.
And that's loud.
No, it's minus 90.
Minus 190.
No, minus 90.
Minus 90, that's heaps.
That was 20 watts from the moon transmitted.
Yeah.
So in fact, there were
That's why it was a noise-free image on the TV picture.
well from Mars, amateurs were picking it up.
Yeah, yeah.
There was an amateur in
Only free
the
space
US
lots.
in Kentucky who actually listened in with his backyard antennas, yardies, to the air-to-ground audio. One way from hearing the astronauts talking back to Earth, but he could hear it. There's a lot of static in it, but he could do it. And he just had backyard equipment. The moon is nothing for us.
Well, it's free space, there's nothing in the
Yeah,
path.
it's very little. Just the Earth, the atmosphere, that's it.
And about 5 million satellites now.
Yeah.
So when you study the pulsars, do you have a particular preferred frequency that you would be studying at?
Well, most pulsars, they diminish pretty quickly the higher the frequency. The best frequency is around 400 megahertz, but that's wiped out for us now.
You don't use that, okay.
Just
Too much.
Too much noise.
too much RFI.
Yeah.
And getting worse.
We have, but 1.4 gigahertz is reserved astronomy band.
Yes.
And so we built receivers to study the hydrogen H1 signal, and with the multi-beam, and we did the survey with it, and then we piggybacked, if you like, a pulsar survey, and we found a lot of pulsars.
So the neutral hydrogen is not wrecking the pulsar detection at the same frequency?
Oh, over the top of it.
No,
Because there's two sources, the neutral
No,
height.
we're just observing at the, no, oh, well, you're looking through the galaxy, so that's why your signal will be dispersed through the interstellar medium and so on. Okay, but but you're looking at an increase in that, that's periodic. So that's why you need to do calibration first, and then you can do it all, so it's not a problem.
Okay.
But if yours is at 1.4, that's good.
Yep.
You shouldn't have a problem. With Vila, shouldn't have a problem.
We stepped down from 1.4 to 70 meg up at the receiver box, and then 70 meg down into the lab.
I say UIF, bring it down to my
Yeah, we've got a front end and a back end.
Yeah.
We've still got to tidy up the front end and.
So what's UIF? 70 megahertz, is it?
Yeah.
That's all right.
The back end is an old analog back end.
Yeah.
We're still going to use that, but we are looking at SDRs for a back end. When you talked about SDRs earlier, we were saying put the SDR at the feed point.
Is that what you were suggesting to do?
No, the SDR,
Have
have
an
your
LNA.
antenna.
You want your
Have
LNA
your
up there.
antenna, and you just put it straight into your.
Have an LNA at the feed point, come down and have the SDR somewhere else.
That's how we were looking to do it.
Confused me.
Okay. The shorter the distance, the better, because you're not introducing all your transmission line losses and things like that. But then it's a trade-off with how much noise you can get from the SDR interfering with
Well,
everything
The SDR doesn't sit on its own, it's got to have a data cable going to it. So you've got all this hash
USB.
sitting at the feed point.
you do. You'll find that, so USB and things like that use a lot of differential signaling and things like that. So they don't generate that much hash. So
But the
they're-
computer you connect to it.
yes, you really connect to and stuff like that.
Even a Raspberry Pi would be
Yeah.
a problem.
So for a lot of if we take the case of the 12 metre, you'll have your receiver, you'll have your LNAs, okay, and you'll get an RF signal coming out the other end. What we do with that is that we turn that into fibre optic signaling
Okay.
and send the fibre optic RF over optic all the way to the tower, and then we deal with it in there. And things like that. Now, those solutions are becoming cheaper, quite cheaper, which is quite surprising now. So that is a way of actually moving all your noise and stuff away from things.
Yes.
So you're going to have a trade-off. So you can have a long cable with your RF going through, then your SDR sitting in a box far away,
Yes.
and your computer and all the noise and stuff that's happening.
Yes.
But the trade-off is that you're going to have this cable running around, and you've got to be very careful. You don't kink, you don't run past power, you don't run past
Believe it or not,
even a shielded cable.
we actually have an optical solution available to us. So it's something we may redeploy.
And so for us, we used to have heliacs and all this RF stuff to transport everything,
Yes.
and it's a nightmare. It's absolute nightmare. Since we've gone to the RF over optical, it's just
So isn't it like 22 gigs straight into the optical fibre?
no. Well, you'll be hard pressed to get something. Sorry, you can. It's stupidly expensive.
Yeah.
Usually we'll IF and drop it down and use
So you've got LNA, convert it to something lower, then optical fibre.
Which is what we did that. We did that.
Yeah, have a look at the
L6
specs of the
development.
SDR if you're going to use it. See what frequency range you will accept. You may have to down convert.
We have one. We have a good one. It's 14-bit resolution, and it will go from
Wow.
10. It'll go from 1 kilohertz
Mhm.
to 2 gigahertz.
Okay, so at 1.4 you could put the RF straight into it then.
Yeah.
If you go to anything higher, you'll have to down convert it to get the RF in.
So with those,
And you know, have a look. Sometimes with the really high frequencies, you know, see what the response is to it. You know, because it may be better to down convert it.
I think we need
just
to
your bandwidth is also going to be important. So I've seen some of those SDRs like that, but the bandwidth is like 5K.
The one we got is the product RSD. It's an SDR Play, and it's an RSPDX.
Yeah.
And that can have 10 megahertz.
Yeah, so it'll be 10 megahertz.
It depends a lot on your PC that's running it.
Yeah, well, yes, because it's gonna do something with the data
Yeah.
that's coming through. But just be careful if you can find. I mean, going down to 1 kilohertz is, I don't know.
Well, that's academic, but
Yeah, it's academic, but bandwidth is important.
Yeah.
The better bandwidth, the cleaner you'll get from your receiver, as long as your front end has actually got that sort of bandwidth also. But the more bandwidth you've got, better, which means more data that you're going to have. And then your resolution, 14-bit resolution, then makes sense. If it becomes very narrow and you've got 14 bits, you're getting a lot of noise, not noise, but you're getting a lot of data bits that you can't do much with.
thank you for that.
Well, I can put you in touch with people who
Look, we'd love to establish some contacts for ongoing support. And, let me know.
let me see what I can
With our, as you say earlier, that amateurs often discover things as we're looking all the time.
Yeah. I mean, it'd be really hard in radio it'd be hard to discover something in radio, but what you could contribute to is the monitoring of things,
Yes.
because you have the time and professionals don't.
Yeah.
You know, like a good example, you know Trevor Barry? He's from Bathurst, not Bathurst, Broken Hill. And he would, and or even Anthony Wesley, you know Anthony Wesley?
Yeah.
Yeah?
That man rings a bell.
These guys just image the planets every night. You know, these guys, they'd be up all night with their videos, imaging and producing these images. And then Anthony Wesley, for example, he'd find all these impacts on Jupiter. And Trevor Barry would observe storms on Saturn. You know, and they have contacts with professionals, say, hey, something's just happened, and then the pros are, oh, right, get the Hubble onto it quickly, or Cassini. Because Trevor was working with the Cassini imaging team, with JPL, before they crashed the thing into the planet. And he would alert them to know what to point to, because they don't know if there's a storm on this, so they have to know whether they should be pointing at the storm at the next pass or something to get better data. And so that's how they contribute, you see, by monitoring these things, because they have the time, and then they work with professionals, and they say, hey, that's really great. So what you would do is I'll put you in contact with some radio astronomers, and then they'll say, look, you know, we want to do this, but we don't have the time. Do you want to do it?
Yeah.
And then you could get involved, and then so okay, then this is how, and then you can come up with a scheme together.
Yeah.
You know, they can see what you've got, and suggest a way for you to monitor it that's useful for them.
Well, we're trying to do things as scientifically as much as we
Yeah,
can.
like for example, I
Yeah.
monitor the Vela pulsar, right? So I'm biased when I said
Yeah.
because you know, I want to find that glitch, right? But I can't do it all the time, okay? So if we can work with people who can, you know, it doesn't have to be Philip doing it, or it doesn't have to be you, but if you've got a team, you know, you say, okay, then you have a roster that says, you're going to do it tonight, you're going to do it the next night, and so on. But you're able to get it done, because you have the instrument, and the time on it, and that's the way to go.
But also, the capability of our laboratory is quite sophisticated.
Yeah.
We have a time reference.
Yeah.
It's good to 10 to the minus 12.
Well, that's what
So
you
we can
need.
timestamp data so it'll be scientifically
Yeah.
usable.
Yeah. Well, I said, Steve Olney, when he was doing it, he was just doing a simple thing and plotting it. He wasn't doing it in the form that's useful for us. It ended up being useful because he could tell us when it happened. That's when it was useful. But we couldn't do much with his data other than that. But since then, he's been working with George Hobbs, my colleague in Sydney, and they've now suggested ways for him to change his system, his setup, and given him software and so on, so that he can put it into a format that he can use if it happens next.
Yeah.
And so he's learned something from it, and George and the others are getting some benefit out of it too. There may even be a little bit of funding we could get if you do that, you see. I have to think about that, you know, because if you can suggest a project that's useful, you know, it's not going to be hundreds of thousands. It'll be maybe a few $100s or a thousand here or there. Any for you guys, anything will be great. Or they may have surplus equipment they can give to you.
Yeah.
You know, they say, use this. Even coax would be good. So that's what I would suggest. Okay, so what you should be doing is get the system, observe something to demonstrate it, and then we can put you in touch with people who can then say, okay, do you have a project they can do, you know, and we work with them.
Excellent.
You know, but as I said, I want to monitor Viva, so. And I was using the 12 metre until we decommissioned it, and 12 metre isn't that much bigger than an 8.5 metre. So if I could detect it easily 12, we should have no trouble. What we want to do is see how small a dish we can detect it. How small does it have to be before you can't detect it anymore?
Okay.
Because that's useful too.
We've got a small horn outside our lab.
Oh, they've done it on horns, it doesn't work. It's got to be something bigger.
Sure.
12 metre though, it's got twice the collecting area.
Of what? Oh yeah, but it's not. But Vita's so strong, you shouldn't have any problems.
Is that word Vita again?
Word count.
You were talking about, sorry, Stephen, you were talking about timing reference.
Yes.
So when,
GPS receiver.
yeah,
So Hewlett Packard is intended for mobile phone base station synchronisation.
Yeah.
So it's a double oven disciplined oscillator.
yeah, so
If it loses a satellite, it drops from 10 to the minus 12 accuracy down to 10 to the minus 10. And that gives us a 10 megahertz output,
Yep.
and a 10 meg frequency is good to 10 to the minus 12.
and that's going to your receiver.
And we've got a 1 PPS that we timestamp with other projects we've got going, and it also gives us the clock.
Yeah,
So we synchronise all our computers to the same time.
Well, I think that SDR.
I'm not, because that's just normal IT shit. I'm more worried about your mixer that you've got
That's a different story.
at your head.
That's a free running oscillator at the front end at the moment. So
Oh, so that needs to be disciplined.
yes.
So you need to use that reference because that's the reference you should be using
Yeah.
to have up on the head.
We need to, well, it's not a multiple of 10 megahertz, so we need to create a synthesizer that would create the correct mixing frequency. I've actually proposed this, Phil, remember that? Have the reference oscillator in the lab, temperature stable.
Yeah.
Yeah, it's on our cards to do.
Yeah. So
I'll show you ours.
Okay, thank you.
so that's going to be really important for the data you collect.
Yeah.
So even the SDIs and everything else, you can give everything
Precise frequency reference.
Yeah.
That gives you your bandwidth, and you know where the signal is in reference. The band that you're looking at is the band that you're talking about. It's
The other
not
thing that you're interested in too
here
is
or something
when an event occurs,
or
what was the
kilometres.
precise timing of that event. Yes.
Yes, yeah, no, it is.
So that's what we're doing as well. If we record anything, it'll have a timestamp.
But so our timestamps are binary atomic clock stamps. So they go lots of digits to the end.
Yeah.
But we need that because when we reference with other telescopes, we can actually process the data as if it's one big
I
telescope.
don't think you need to go to that.
You don't need to go to that sort of things, but just having in the electronics chain, having a good reference that works all the way through,
Sure.
it makes the data that you're collecting valuable.
Okay.
As opposed to something that's wandering.
There you go, Steve.
Yeah.
And if you then put that into a format that we can use with our software, even better.
So what format? If you
Oh, this depends on for the pulsars, there's spectral line, it just depends. You know. But if you can capture the data as a time series voltage is just dumpable. We can read that and put it into the format that our software can do. Well, essentially, that's what we're doing anyway.
Yeah.
You know, but we do it on the fly. But if something is found, like at ASCAP, if they suddenly detect an FRB, the data's buffered, and so they just do an immediate dump of all that data, and then they can go back and capture it, obviously, analyse the problem.
So how much,
Requires a lot.
would it be for us to get an atomic clock like you're using?
So
What's your function?
what's it done?
Oh, it's unlimited.
Oh,
So this,
You know where the shelf is?
so there's different atomic clocks, and we only have an atomic. So ours is a tier 2 reference here. It's only because one of our studies is what's called the binary, pulsar time array. So we're referencing time here, and also what we're receiving across the sky from the different pulsars, because we're trying to find a gravity wave. Okay, so you have to integrate all the data, but you have to have really super accurate stuff. So our hydrogen masers that we have here, the one that's still working, is, if you have to buy it from the Americans, it's just put an order in for 650,000.
So you've got one going second hand, have you?
Each? Is that each?
No, one.
Each.
I mean, you can get a rubidium stick.
Which one's not it? What hose are the billion wood?
Yeah. The rubidium, we've got it, but it doesn't have the stability.
Stability.
You basically want this if you want to be phasing across the
Yeah,
globe.
and use it for VLBI and other things.
Yeah.
But for what you're using, if you want to do it, you don't need.
Yeah. You've got too many
We've got what it
areas
is.
in your system.
Yeah, it's
or
total overkill.
That's gonna,
You don't need it.
so your GPS disciplined clock is to a rubidium standard, and that will be more than adequate. But the mixer in the head, because you're mixing it down to an IF signal, if that was locked to that reference, it makes the data you're collecting worthwhile.
Useful.
Just has to be very stable.
It has to be very stable.
Got the point, no worries.
Your IT stuff where you're time stamping the data,
So just
Doesn't
back
matter.
onto that, is that so that you can phase the signals with other sources? Is that the idea? Because I mean, if you want a really accurate, I mean,
Oh, yeah.
basically, if you want, I mean, what you're saying is you really want a really accurate measurement of. Sorry, you really need to know it's at 1.41, whatever the frequency is, and you need to know that really accuracy. I presume, is because if you want to try and phase the signals.
Yeah, because if we
to another source.
if we do a VLBI, we're linking parks with Narrabri,
Yeah.
Sejuna, Hobart, Tidbinbilla, South Africa, Japan, or whatever. You need to know exactly when your wavefronts are like.
So that you
In
can
one
sense
nanosecond,
it huge interval.
It'll travel that far.
yes.
Okay, about 40 centimetres or so. So if you're not accurate to at least that, you're gibberish.
And so our masers are stable, also stable over time. So while your single measurement is accurate, over time they drift 10 to the minus 15 milliseconds. Drift.
Which we have to adjust. So the US, remember the GPS, the US American, they maintain the stability of their clocks on the spacecraft. And our clock, as I understand it, so I could be wrong, we're very accurate at the short term, but over the long term it does drift off, which we then use the GPS to then put back to
And then you have a glitch.
Well, yes,
Which when they found
but
the
in that-
first glitch, people thought there's something had gone wrong with the setup.
Resetting the time.
And in fact, they said,
When we
no,
do
it's fine, it's just
adjustment-
also.
we actually put a marker in the data file saying we've adjusted.
Yeah.
We've adjusted. So that way,
Just
over
about
time,
somewhere from the top of
yeah,
it.
you know what you
So storage of that, what you're receiving, what do you actually,
Discs.
no, what file sort of, do you just have the file spreadsheet type idea, or do you put it into a fixed file, or?
You could if you want to. We have depends on what it is you're doing. You can have an RP fits file. RP is radioactively written by CSIRO.
That's the CSIRO.
Yeah, there's
Sort
fits
of
file. There's RP fits files. There's PS archive format for the pulsars, .rf file, and then there's different formats depending on what it is you want to observe.
We were thinking of storing straight to a database, but is that not a good idea, or
Commas separated
Okay.
data file.
just
Just a simple
text file?
text file. Well, you could,
It's
I mean, you could
it's
just,
file
you
format.
could just have it, well, that's all text, isn't it?
You'd be able to take it from that database into whatever format you want it.
Yeah,
So
to put it
that's
into a
just
file
central-
that we
So-
can read,
So
say
if it's
what
what
you've
you've got,
done.
and then from there we take out.
We can then read that and then put it into the format, which you can then use the software to analyse. Because when I did the 12 metre, I wanted to study pulsars, but we couldn't, it's not designed for that. So we took a little diagnostic board, it was 16 megahertz bandwidth with 1 megahertz, 16 1 megahertz channels continuous. And we just took just a voltage dump of each one. And got enormous files, 1 point something gigs for 20 minutes worth of data. It was big. and then I ran another script that would read that and put it into a format that our pulsar software could then read and produce the profiles and the residuals and other things to analyse it. But I had to figure out what that original format was that it was doing the voltage dump on. And only one person knew how to do it. That was John Reynolds. And I had to pin him down in his office one day and said, John, on the whiteboard, just tell me the format, right? Because everyone I asked said, you can't do it. But he said, no, you can. He said, all right, tell me. And he told me. I then went and told George. And then he wrote the script that converts, and then the rest was easy. Yeah. So we weren't doing it on the fly, in real time, but you would observe, dump all the data, and then run the stuff on that, and then you'd have a look. So when I was doing a glitch, observing field for monitoring for glitches, I would do a 20-minute observation, and then it would take about another 10 minutes to process that data, and then I could see it straight away after that. So it'd be about 25 minutes or so, 25 to 30 before I can see if it glitched or not. And if you did, just keep going. Take as many as you can.
So Phil, that NOAA satellite thing that I was telling you about does exactly that. It dumps the SDR data to disk, and then later on
Yeah, like the one that we've got here, that one there, that we're thinking of doing for the project, is just going to do a dump of the data.
Straight into a ASCII file.
Yeah, or whatever format.
you just do it binary.
Yeah, and it just dumps it, and then they just go and read it and produce what they want.
So reading whatever the reading value is, date, and maybe some other bits and pieces.
Remember, if it's a voltage,
Timestamp date, or timestamp and data, timestamp data. Is that what you do?
Yeah.
well, I'm not sure how they do it exactly, but you have to have the time, and then you just might have a whole series of voltages, but at known intervals, and you just know what it is. I don't know how they do it. Yeah, I don't know how they do it, but but that's how. Whatever it is, they just need to dump it there at some. But once you've done it, of course, you can then run the thing to put it into a pulsar format, or you can do it to put it into a spectral line format that you could observe. And you've got the data there, just the voltage dump, and put it whatever format you want. So at one observation, you can do 2 or 3 types of different observations with it.
So the other thing also with the
One data
SDRs,
set.
if it's off the shelf SDRs, if you have a look at GNU radio, GNU radio, there's now starting to appear a whole pile of astronomy packages.
Oh, cool.
You go in there, so
And they're free.
they're free. So you can actually
open source.
they're all open source. You can actually wire up the whole thing, and I've seen a couple of them where they've got FFTs and they've gone spectral and they've done all this stuff. They've written a couple of modules. Can't remember who it is. I think SETI are now the holders for the GNU radio software package. They're going to hold on astronomy things in there.
So Berkeley.
At Berkeley, yeah.
I've got another technical question about the wonderful dish.
What dish?
Between the feed point antenna, the probe, and the first LNA, is there any RF filtering, bandpass filtering?
One person answer.
No.
Okay.
No.
At our facility at Heathcote, it's a shared property. We've got Wi-Fi systems running 24 hours a day. There's actually a mobile phone repeater system.
Not a place to put the cells.
We are subject to localised interference, and we may face the fact that we're going to have to desensitise the receiver by putting a filter in front of it.
Oh, okay.
Yeah, you will. You will. That's not a problem.
It'll come straight off the
Like just the
sensitivity.
notch filters and things like that.
Well, the bandpass filtering, yeah.
when I'm up there, I use Wi-Fi.
So it might drop the sensitivity 0.3 dB or something like that, but we may be faced with that. At the moment, we don't. So you don't either.
No, so the ultra wide just recently
Yep.
actually put 2 notch filters and to take out the base stations that we can see.
The mobile towers.
Yeah.
Okay. Okay.
And this is the unfortunate thing. The only thing you're going to be able to filter out is the tower, not the handsets.
No, because they're,
Of course,
they're,
it's an uplink signal.
Yeah,
Because they bounce, they
they're
jump.
so close and they're.
But the mobile phone tower will always have a centre frequency because that's what the mobile phone has to find first before they start
The
negotiating.
carrier
frequency.
signal.
Yeah. So we've got a notch filter in there, and surprising for us, we put the notch filter in there, and then suddenly we start to see things either side of that band that we weren't able to see before.
Sure.
Because the signal's so bright, it's saturated.
Good.
So even with notch filters, you'll be able. That's in your analog part, so where your LNAs are.
Yeah.
That's where you'll put your filters in. And it's still possible to do work in that space, but you're going to have to be very selective with your filters and things and work out exactly. So the tower that's next to you, find out exactly what that frequency. So go to the ACMA website. It should tell you what frequency that thing is running at.
I worked in the cellular industry for many years, so I know what you're talking about.
Yeah. So for us here, we knew what bands they were in.
Yeah.
And because we can't see them, we actually could build the notch filters.
You know, the buggers keep changing the frequencies too. Doesn't stay static.
No, it doesn't, but well, that's where we're lucky here. Our country ones stay pretty static.
Yeah.
They don't
Capital cities, a big difference, yeah.
mainly because they've done a lot of modelling on these ones.
Actually, you can see this is the first FRB discovery.
So because it's got a bigger footprint, it's bigger
It's
sensor.
first, and
So they want
it
exactly
increases, gets wider.
for this sort of volt type.
You're probably being a little bit protected too, knowing that you're here. They're
No.
not going to fiddle with the network.
No,
They don't care.
There's a requirement for them to let us know if they're doing it, and then we can suggest things.
we suggest.
I'm
We
glad
can't stop them because they're legitimate users of the site.
Yeah.
But you know, they usually, I'll say they are understanding.
Yeah.
They'll do their best for us.
Just
We can say do it at this frequency rather than this, you know, because that'll be easier for it. Because if there's a choice, they say use that instead.
Yeah.
Because that way it won't be as big an impact on us,
Yes.
or it won't impact at all. This one will.
I'm glad to hear that.
So you can always point your antenna at their antenna and run yours in reverse. You guys would win.
We may incinerate if we do.
Pew pew.
Yeah, but that would
Do you
backfire on
employ
us
programmers
because we'll probably burn out
to
our.
work with your
antenna?
particular equipment, computer equipment?
The what, sorry?
Do you employ programmers who will work with you?
Oh yeah, it's
almost.
almost everyone that.
So when you write these data files to your computer and you've got the 1 pulse per second signal to go in there, you're going to lose a little blip every second of data.
Sorry.
So when you write your data to the computer file, supposing it's an SSD or a
Oh, I see what you
multi-
mean.
Yeah.
every time you put a blip on that pulse, you know, say this literally 1 second, you're
No.
going to lose a bit of.
No, we don't stop. We don't stop taking data while it's writing. We just keep buffers and just writes it continuous.
And in fact, especially with ultra wide, there's actually a figure that goes in there that goes. It takes so long to get through digitizers and actually get through the optical fiber all the way, you know, from the RF to the optical fiber to digitizers, and then from there to actually writing it. That we actually put the timestamp for that delay. So what you would think when the data comes,
Yeah.
that's not the timestamp. It's we actually go, oh, that actually should be about 40 milliseconds before, and that's what the timestamp is exactly. So we actually timed that so that everything that gets written to disk, written to memory, is actually got the right timestamp on it.
So you've got some really good equipment left to buffer it and everything that you want.
Yeah, so most of the stuff is most of our in the ultra wide in particular, they're all FPGAs systems that we've got in there. So they're all designed to do that sort of work and keep the timestamp.
Because we've just got laptops.
Yeah, yeah.
No, that's all right.
Yeah, so that's not a huge problem with the data you're taking. I mean, we have to be a little bit particular because of the range of things we have to do. For your the GPS locked timestamp, there's NTP and there's a new standard for NTP which is for real time. That would be probably a nice thing to move to.
I don't know that, Phil.
Yeah, I'm running that, yeah.
What do
But you got to play with the network a bit to make sure that those data packets come at the right time. And it just means your whole network
Yes,
changes.
jitter and stuff.
It's very strict on the timing for those things.
Jitter.
So,
You can worry about that much later, just get your system away.
Yeah.
Well, that's
Yeah, so the element,
yeah. So also remember, you just don't have pulsars from.
Yeah.
I mean, you've got.
We have a wide range of projects ahead of us,
Yeah.
including Earth, Moon, Earth, radio contacts and things
Yeah.
like that.
You also got planets. You also got the sun.
Yeah.
Yes.
Just be careful with the sun.
Equals 30.
Because you point direction with, you point directly. You know, the dish is a white surface.
No, it's not. It's a mesh.
It's a mesh.
Oh, it's a mesh. Okay, that's even better. If you have a solid surface, that can be.
Oh, the actual
interesting.
reflection with deep.
Yeah, it can be very interesting with your
So the guy have to wear it in front.
We certainly saturate our neutral hydrogen receiver when we point it at the sun. We've seen that.
How heavy is that, is your receiver at the top?
Sorry? Oh, how heavy?
Yeah.
it's
Small,
more,
it looks pretty big.
I'd say 50
it didn't
kilos.
actually weigh 50 kilos.
It's inspired from this thing here.
It's two-story mice.
I can see
Is that with or is that with or without the bird's nest in the feed horn?
Stevie, you have a question?
I had a question again about the wonderful dish. Obviously, there's issues when you point the dish towards the horizon. What is your sort of limit from here?
Well, we only tip, see, as there, it's tipped to 30.25 degrees elevation.
So that's the physical limit anyway.
Yeah. Now,
No, we can go a bit further
you
down.
can go a little bit further, that's where the software takes you to.
Okay.
We could go even lower, and go to 29 point something degrees elevation, where you literally will hit the concrete.
And that's still receiving.
But the reason we limit it, there are two reasons. One, when they built it, they didn't have quite enough money to build the tower big enough to tip it further. But also, if you tip it too far, you start to get spillover. You detect radiation from the ground.
Well, that's what we're seeing.
That's what we're seeing.
We seem to get
So there's
at
only
least to 20 degrees, we seem to find.
Yeah. So below 20, the ground is the hottest thing around.
Absolutely.
So that's
so you are limited.
Yeah. Okay.
So I mean that's why they stop there. For spacecraft tracking, they want to go down as far as they can
Into the horizon.
to pick it up as soon as they can. But remember, they're observing spacecraft on the scheme of things are very close, and their signal's booming compared to everything
So it
else.
overrides the surface.
So they doesn't worry, and they use such narrow beam widths.
Yeah.
Okay, bandwidths.
Mm.
They literally down there to just to a few hertz, gauge them and lock onto the signal and they can follow. And so they're not all that concerned. Okay, but for us, we do radio astronomy, we're trying to pick up the weakest signals you can imagine, and we don't want anything interfering with that. And so for various reasons, they stopped at 30 degrees for us.
Okay, so just on that, the dish itself must have a thermal noise as well.
Yeah.
The actual surface of the dish.
Yeah, it's all
300
factored
Kelvin.
into
It's probably an emissivity of about 2% or something.
Yeah, I don't know what but it's all factored into.
So that just provides an offset.
Yeah, you do an observation and you get your baseline. You don't have to got that.
And I guess that's the value of the
That's one of the things we were looking at. We have done some sky surveys and they get different results each time. Is it, do you take your values as a...
What do you mean? What survey have you done? Just
We did the Large Magellanic Cloud.
scan across it and so.
Yeah.
Do you calibrate every time?
Oh,
No.
Yeah, so signal is in reference to the signal that you've done. So the one before it, that's the reference you've got.
yeah.
Imagine trying to take a picture of imaginary cloud at midnight and another time, during twilight or whatever.
Yeah, it's always different.
It's gonna be different.
And that happens to
But
you
you've got-
with your...
Well, we calibrate everything, so,
Yeah.
and then
So you get a different value coming back each time we look at something.
If you don't, yeah.
Yeah.
Yeah. Well, it will be different, so you have to calibrate it, so you know what is the actual flux that we're receiving.
So it's all
So-
relative,
So
Yeah,
not an absolute.
there's a little subtle thing that you've got to realise also, is that if we see it different because we've calibrated our receiver,
Yep.
we can now say that that's something significant.
It's variable.
Hmm.
It's a variable
So
source.
the power output of whatever we're looking at has changed.
Yeah.
The signal that we receive has changed, and something between us and whatever we're trying to look at has changed. It could be the source, or it could be something in between. But we know that
Yeah,
that's,
that's the actual receiver.
that's why we have to calibrate all the time.
You'll have to calibrate, do a lot of calibrations.
'cause you- and-
I mean, when you do surveys, there's calibrations all the time.
Okay, so we need to get a diode. Set it up
Well,
or whatever.
Or you just look at a
Some
source
idea.
that has a point source that's of a known flux density, right?
Yeah.
And you like
And
Fornax, Virgo A or Fornax or what, some point source.
And even though we're getting a different value on our receiver, we then say, oh, that value is now real
Fractions.
what
You
we're
can
looking at.
adjust.
three,
That's
three,
right.
yeah, 3 volts on.
It's got to be a point source and constant. You don't want it to vary. So you know, and people have measured it, so you know what your flux what your flux is from that, and then if you go and observe something, okay, we've got something we go back.
So a nice
Yes.
source is Jupiter.
Oh,
Jupiter does vary a little bit depending on the frequency.
Yeah, on per frequency.
We're talking
Yeah.
hydrogen lines.
But also
I've
not
seen
all
some
that
examples.
difficult.
There's sources you can because we have to do it all the time. In fact, I was doing it yesterday.
Yeah, I think we've got
Had to
those.
produce the flux calibration files. Astronomers were saying, where is it? Oh, I'll do it. So, but yeah, you have to do that regularly.
So, on that same line of thought, neutral hydrogen signal itself, that's one of the things we really keen to survey our southern sky, map the whole thing, have a beautiful presentation, and show that our telescope is worth something. But is the signal of the neutral hydrogen, does it remain the same intensity day after day, or is there other periodic changes in that intensity?
No, it should. Well, if it's properly calibrated,
Yes.
it should be the same. But depending on where you are, you're looking through different parts
Of course,
the
of course. So it's a different intensity.
Yeah,
So there's no
and it'd
underlying
be slightly different frequency
periodic
too.
variations or...
It would be a slightly different frequency because of the Doppler shift.
Yes.
Okay, so you've got to take your motion into account.
Yes, yes.
Okay, so you've got these are the motions you've got to take into account. Okay, you got your rotation,
Yeah.
you got the movement
Progression.
around the sun,
Yeah.
you have the movement of the of the solar system
around.
around the galaxy. So you have to compensate for all that. Okay, and to get the correct frequency.
So the frequency will be changing over time.
Every
the
6 months.
frequency on one particular should be the same, but depending on where you're looking, if you're looking through, let's say there's a spiral arms, right, and you're looking at it like that through a cross section of those spiral, then each spiral arm with neutral hydrogen in it will have a different velocity away from you or towards you,
So that's your
and that'll produce a Doppler shift.
But the Earth's spinning and
Oh yeah, but you've got to factor that
so
into
that will
it.
change its frequency.
That's why you need to know the time.
Summer, yeah.
Every
That's
six,
why you
every
need-
6
yeah.
months.
Yes, neutral hydrogen will be,
Certainly
One
give them something
frequency.
that will work.
but what you will receive is a whole range of frequencies,
Yes.
and then you've got to work out from the intensities, what are you looking at? What is it, just our rotation, or is it a spiral arm, or is it,
But the intensities of that particular thing should stay the same.
Well, yeah, if it's a constant source.
Frequencies will shift because we're spinning and.
Yeah, so the only time
Yes.
that will vary is if you've got a cloud or something that moves in front of your source. So
I mean, probably not that great because we're looking at galactic.
That affects it then. Cloud.
yeah, well, it's a molecular cloud,
Yeah.
as in space.
Oh, you don't mean clouds up here.
Clouds
Oh
are.
no, and L-band,
We're looking at
there will be, at L-band, the cloud will have slight attenuation, not much. It's the high frequencies that.
So it only attenuates, it doesn't matter.
If it goes larger, you've got something else happening.
That was a different cloud.
It should be the same if you properly calibrated to take it out of it.
It should be.
Taking out the motions.
We've done it right.
Yeah.
I mean, might have to speak to a real galactic astronomer and tell you, if what variations to expect.
You're the pulsar man, we talked to somebody else for the galactic
Yeah.
thing.
And,
I mentioned these.
but but they'll not tell you exactly, but even in pulsar astronomy, because you're measuring things super precisely, you have to know exactly where you are. In fact, we don't even, we measure the signal when it arrives here, but we reference it to the barycenter of the solar system. So we have to know exactly where the barycenter is.
Which is not where the sun
Is that
is.
good?
Well, it does, depending, well, our knowledge of it does shift, because remember, if you've got the mass of Jupiter wrong,
Yeah, that's what I mean.
okay, then your barycenter is going to be somewhere else, okay? Okay, and so what we can do, what we have done is we've observed pulsars and made all the corrections, and if we still see a periodical shift in the time of arrival, then we can say, let's say it shifted about every roughly 11.5 years or whatever it is.
Okay.
We don't have the mass of Jupiter correct.
That's
What should Jupiter's mass be to remove that periodical
Yep.
drift? So we can correct for Jupiter's mass. Okay, and then we did it to Saturn about 10 years ago. We had enough data to correct for Saturn, and we got a better value than any published value of Saturn. Although JPL had a better one. But
So how far was the barycenter shifting?
not much, just a few
Meters?
meters.
So it's basically round about the middle of the sun, give or take a few.
No,
It's not.
It's actually outside the sun.
Yeah, it's just outside.
Yeah.
It's in between, somewhere in between.
Reference everything to that. So you have to know your altitude on the Earth. You have to know your latitude exactly. So you need to know your velocity. You need to know the orbit of the Earth very precisely. So you can measure the velocities. You need to then know where all the other planets are. So
You've
you
got
know
to
the
be
reference.
calibrated.
And then you have to do that relative to all the motion around the galaxy. And so, yeah.
So what accuracy are you measuring at the time?
Oh, our timing it's just a few nanoseconds, right?
Is that reference to the VS Amora, is without all correction?
The what, sorry?
The VS Amora,
Very large,
Oh, VLA.
very
VLA,
large
well, it's
array.
like our compact array. You need the time to do the cross correlation and antennas and so on. Yeah. You have to phase them all correctly. So you need a really accurate time span for that. And in fact, you can actually see the results changing at the compact because it's 3 kilometres, 6 kilometres, the biggest baseline they have there. And on a particular day, it could be warm and temperature changes over time and so on. And so you see the thing changing that way, constantly corrected.
So when you're measuring the basically when you're picking up a radio signal, it's essentially it's noise that's coming in from
Yeah, we just want to measure the
So what's
voltages
the
and
distribution of that noise? Say pulse heights or peak heights or something. Is it like stop noise distribution?
Oh, I don't know.
Yeah. Is that a useful thing to measure, or you just
So, pulsars tend to be cyclotron
okay?
signal.
Yeah.
So they'll have that power spectrum. And different signals you'll get will have a different power spectrum, depending on whether it's thermal. So stuff like XAJ will be thermal mostly. So it won't be synchrotron type thing, which will have a different sort of pattern to it. So, but you only find that out when you start doing spectrum work. Pulsar work is very much about looking at regular pulse things and adding them together so you can see that signal creep its way out of the noise.
Does that always imply that you need to know the frequency before you?
Yes.
Yes.
Yeah.
Well,
So when you do a search, you just sit on a point and you just take, like I said, just a voltage dump, and then you then search on various frequencies. So you fold on various frequencies. I'll try 1 second.
Okay. Yep.
Average it all out. Do I see a pulse?
See something.
What if I do 1.001 seconds? No, nothing. just go through all the periods, you know. And then there's dispersion, depending on how much the signal's dispersed as it's travelling through the stellar mix. You've got to correct for all that. While you're doing all those other searches on the period. And then, so and if the thing's orbiting an object, it's accelerating, so it's changing. And you go, oh my God, you know. So the computation is enormous, just to find one. Because in the old days it was easy. You just had a chart recorder. In fact, just try a chart recorder, guys. What did I think of that? I mean, I've observed it on the chart recorder. You can see the pulses on a chart recorder.
Wouldn't you have to search just in case there's more than one frequency?
Oh yeah, in the old days they just had a chart and just scan it, and if they suddenly saw the pen go, oh, there's something there, okay, and then they studied it. Now, well, we found all the bright things. You know, that's how Vita was found when the chart recorder was so bloody strong. Couldn't miss it. But
But they did.
oh yeah, because they said they smoothed the data around. Don't do it. But now it's all digitised. You just have to take a big bulk and just do a search on it. You know? And that's really computationally intensive. You need a supercomputer or a system. But if you know roughly where it is, you know, and you can get a good guess, and be lucky you'll be close and you'll find it quickly. Otherwise, you just have to search through the whole thing. And so when we did the multi-beam survey, started that 25 years ago. You know, we found all the really obvious ones, and then, well, we kept all the data, the raw data, and then people then, once the survey was done, other PhD students go, and then went through that, and they found another 300 or 400 pulses that missed on the original one, because they come up with better search algorithms and so on. And now with AI, they're searching it again, because things that we may have missed just looking at the data, the human, you know, tired and bleary-eyed and not quite understanding what he's doing, or the AI now learns and it's, oh, we found a few more. And in fact, the Chinese, we're working with China to do that. I don't know if it's that, don't recall that. It's a good thing to do, but doing AI learning to search for these things, you know. In there, they have the 500 metre synthesis telescope.
Fast.
Our telescope would be smaller than the focus cabin in its relative size. Yeah, well, yeah, we're fully steerable there. But anyway, yeah, they don't want to find these really incredibly weak pulsars and so on. And so they do, and then they follow up with us.
Okay.
So we're working with them, and they're developing these AI software to find these even more. So we could probably go through the data again and find lots of things we missed originally. Which is why you never throw your raw data away.
Which is unfortunate because.
But in the old days, yeah, one file would have been maybe 2 or 3 gigabytes, right? But now we'll be collecting them at 9 terabytes an hour.
Now,
Once we get the new one. So
That's what I want.
Yeah.
I think we need to update.
Huh?
I think we need to update.
On a USB stick.
yeah. So our new receiver that we're hoping to get later on this year is so, whereas ultra wide has just got one feed port, that's got 72 in an array. So it's a phased array receiver, and that's the data rate that comes off that is phenomenal. And that's like ASCAP in WA has 36 antennas of the same thing.
yeah, they have the Mark II PAFs, which only gives you 36 beams on the sky. The one we had here, the Mark I, gave us, we could generate off the hands, just a smaller number, so 6 or 8 or something. I only ever used one when I was doing overkill for the rest. But this one will be 72 beams and cryogenically cooled. The others aren't, so even better, which is why but the data rates are enormous. Yeah, we can't even ship them off site fast enough before we have to record more. So
I have heard that if you run out of disk space. The universe doesn't change that much. You can store it.
Well, hopefully nothing significant happens while you're deleting everything. You think this is,
Yeah.
oh, well, we just miss it, you know. It'll be exactly where we are now. So, you know, but at least we will, some of the time we'll be able to find something. We'll have the opportunity to find something. But yeah, but I think it's almost lunch now. But what I'll say is, when you're thinking of these things, first thing is just get the telescope to work, record something. Vida's a good one. Try for Vida because it's,
Your favourite?
yeah, it's my favourite. It's also a very strong signal.
Sorry, what was it called?
It was called the procrastination pulsar.
But the thing is, get it to work and then get in touch with professionals and work with them, because what you've got something that they don't have, you know, time, you know.
Well, we've only got 1 weekend a month.
Well, can you do it remotely? Can you operate it?
Yeah,
Easy. So you have time and they don't, you know, and always think in terms of, you know, Trevor Barry and Anthony Wesley, you know, they're amateur video,
doing it all the time.
they're doing, monitoring all, they find something, they hang out, they'll work 2 years for that one little impact that lasted all of a second or so, and then, oh, well, it's worth it, you know, and they get their name on the paper and they've contributed something significant, which is really good. But you can do that with radio astronomy too. Now, that simple radio telescope we built at Narrabri, no one expected to be doing this with it. It was just a little demo for schools and the visitors, and yet they would contribute to the strength of the solar flare, which is good. And Steve Olney was able to monitor Vega for us, you know, and well, he did it regardless, and then told us, and they said, oh, thank God, we've been monitoring, we missed it, but you got it. So we knew exactly when it, or close, very close to when it happened. And they're the kind of things that you should be doing. I mean, it's always fun to detect the hydrogen line, but I mean, it's like looking at Alpha Centauri through the telescope, or Saturn for the rings for the first time. You go, wow. And then what do you want to do?
Yeah.
And then what?
We're still at that way out.
Yeah. So, I mean, everyone wants to see that hydrogen line. They want to see that pulse or that nut they've produced. But then what do you do with it? You know, for most people, the fun is in getting it to the stage where you're seeing these things. It's like building a telescope and then going out and looking at Saturn. I built that.
Well,
you know.
yeah, we've
That's cool.
recently, in general terms, it's taken us nearly 10 years to build this thing,
Yeah,
and we're just now getting it to work properly.
yeah. And technology's advanced ahead of you.
Yes, it
So
has.
now you can almost do away with a lot of that analog stuff.
It's making a clunking noise. Or
Yeah, there's a
Yeah.
mechanical issue.
But that's my point, you see. So different people have to. Some people just want to build the thing and they get the pleasure out of that. Others want to use it to do just to see something, and others want to use it to do something useful. You know, that will contribute to science.
Well, that's
They produce it. You know? So, well, you know, I can put you in touch with people who'd be happy to do that. You know, I mean, there are a lot of. I'll email them to you.
That's fine.
But there's a lot of projects you can do. I said, I'm the one I have, the Vela and the FRB was what I was thinking of doing with the 12 metre. I did Vela, but didn't get around to doing the FRB stuff because of COVID. But there are other projects you can get involved in that you can contribute, and so I'll put you in touch. But just think along those lines, because an 8.5 metre rate is not a small antenna. It's actually quite good.
Yeah.
So, perhaps a closing question, John, if that's all right. So what's the Parks Dish project currently working on?
Oh, what time of the day is it?
It's a multiple project.
Oh yeah, we have you can have a look outside, but astronomers all right across Australia and the world, every 6 months they submit their proposals for projects they want to do. It then goes to a time allocation committee made up of local and international astronomers who appraise the projects on its merits. It's blind appraisal, and if they think a project is good enough, they give them the time, and then we notify them, and then they come in and get scheduled in, and then they come on the scheduled time, do their observations and acknowledge us using the telescope, and we don't charge them for it. It's called the open skies model. So in that way, any astronomer, regardless of where he works, whether it's a big university with their own facilities or a small department with nothing, they all have equal access to one of the finest instruments of its kind in the world. But we also have overseas astronomers, and we treat them the same way, and we don't charge them for it either. But when we do that, we expect the countries to reciprocate, let Australians use their facilities. And so in that way, everyone benefits, but it also means that, you know, you're not building, you don't duplicate facilities everywhere. We don't have the equivalent of 10 Parkes telescopes everywhere. We have the one that everyone uses. Another country will build to its strengths, what they're good at doing, and everyone gets to use that. So in Australia, we lead the world in radio astronomy. We help found the science, and we're recognised as undisputed world leaders in it. So the world looks for leadership in the field. And so we in CSIRO aim to provide that through facilities like Parkes, Narrabri, new instruments in Western Australia. Other countries would build it, like the US would build space telescopes and put them up there. Or basically, but other countries would do, like the Europeans are really good at optical because they have facilities in Chile and elsewhere. And in that way, you just have a greater variety of instruments to do research. In the past, you would have been an optical astronomer or a radio astronomer, and never the twain should meet, as they say. Radio astronomy started because optical astronomers didn't understand electronics. You know, they had no idea what the radio engineers were talking about. You know, flux densities and this and that, and what the hell are they going on with? And but nowadays, if you're an astronomer and you're not observing in different frequency regimes, you're not doing your work. You're not going to get much work for your next job or whatever. So most astronomers now would be observing in radio. They'd also have follow-ups on optical telescopes or X-ray or gamma rays or ultraviolet, infrared, you name it. Whatever they can get their hands on. And they work collaboratively too. So you might be a radio astronomer, Stephen there will be a radio astronomer, and someone there will be an infrared, and they'll work together to know the problem and solve it and write a paper and so on. So in the past you would have had papers with maybe one or two names on it. Now you have listed out the song and all the names.
First page is all the names.
And right down
Every
the bottom
time.
there's a Sarkissian there somewhere. You know, so yeah, it has changed, you know, but there's lots of projects you can get involved with. Because as I said, you have a commodity that they professionals don't have, which is time. And you take advantage of that. And if you tell them, look, we can monitor this 24 hours a day, you know, 7 days a week, you know, or at least half the day, you know, when it's up.
We'll aim to, please.
Yeah, and then get involved, and most of they won't say no, because what's there to lose? You do it. If you find it, then tell them, and they'll use it. You know, there's not much to lose in collaborating with you. So that's what I'll do. But investigate the SDRs too, because it's an inexpensive way of doing it, and you can do different things with the one SDR.
I'll just download the radio on mine as well.
On behalf of the ASV, we thank you for giving
I'm
us
sorry,
this
I'm not an electrical engineer or a radio engineer. So some of the questions, I just use the equipment.
We just love
I just use the equipment, and we have brilliant engineers that do the software and the hardware and everything. I can put you in touch with them.
this was fantastic.
Maybe
Really appreciate it.
Yeah.